Learning target number 30 is about gravitational potential energy. Now, in looking through the equation sheets for the AP Physics B test, you'll notice that we actually have two different equations for gravitational potential energy. And they have a little bit different form. First off, this one it specifies as the change in gravitational potential energy. And this one is just gravitational potential energy, just some value at a certain position. Gravitational potential energy is energy associated with a system of at least two objects that are pulling on each other because of this force of gravity that exists between all objects with mass. So we have two objects with mass, and they're separated by some distance r. Now, if we look at something that's changing position, a system where those two objects are changing position relative to each other, but only in small amounts, small compared to the overall distance between them, then we can simplify this equation down to this one and figure out the change in gravitational potential energy due to this small change in position that we call h. Usually we think of that as the height above the surface, typically of the Earth, is where we would use this problem. So g is going to be the negative 9.8 meters per second squared. We just use the positive value there. M is the mass, and h is the height. And then typically we would do this for two different positions. Often, though, we just set the height equal to 0 at one of those positions. So maybe we're jumping from the ground upward. We would say the ground has a height of 0, and then our upward position would have a height of not 0, and then whatever the new height would be, that's going to be equal to the change or when we calculate it, that'll be equal to the change in gravitational potential energy. If we want an actual value for gravitational potential energy, though, this equation is the one we're going to have to use for the potential energy at a single position for these two objects relative to each other. Now, typically in physics, we would have used this equation, not AP Physics, but regular physics. We used this equation, and we would have talked about the potential energy of a single object above the surface of the Earth. That's not really a correct way to express this. The energy happens because of the position of at least two objects, the position of objects within a system, and those objects are exerting this force of gravity. So between any pair of objects, this equation gets us the gravitational potential energy for that system, for the system that just has one pair. Now, these two equations, since they're both for gravitational potential energy, they should give us the same results. So let's just check that works out. We'll do a simple case where we have somebody who's going to be jumping upward from Earth's surface. We're going to look at what their change in gravitational potential energy is when they jump. So we'll say this person has a mass of 65 kilograms. We know g, the acceleration of gravity, is 9.8 meters per second squared downward. The initial height, or h naught, we'll call 0 at the Earth's surface, and it's going to jump up 1 meter. I should make that 1.0 meters. 1.0 meters upward. So this one we'll calculate first with the simpler equation, the one that you would have seen in regular physics. We'll do the mass times the free fall acceleration of gravity times the height. So the change in gravitational potential energy is going to be 65 kilograms times 9.8 meters per second squared times, really this is height final minus height initial, but our initial height is just 0. So this one we're just going to do 1.0 meters. And for delta UG, the change in gravitational potential energy, we get 637 joules. Now if we go to the other equation, there it is, we'll need this information. We need the masses of each object, we need the distance between them initially, and the distance between them in the final state, and we need the gravitational constant. And then here we had UG, not delta UG, but just UG, is G, the gravitational constant, times m1 times m2 divided by r, and we have this negative sign on it. And the negative sign makes it so that the change in gravitational potential energy will be the same in either system. So as r increases, we get closer and closer to 0. So when our objects get infinitely far away, our acceleration of gravity, our potential energy from gravity becomes 0. And as we get closer, it becomes more and more negative. So that corresponds with our potential energy from gravity being 0 when we're at the surface, in the old way of thinking of this, and getting more positive as we got higher up or further from the surface. So here, if we want delta UG, we're actually going to have to calculate this twice and subtract. So we'll do negative G m1, m2, and then we'll just do 1 over r minus 1 over r naught. So the m1, m2, and the g, those won't change, so I just factored that out here and made this, instead of r, made it r and then minus r naught. So this one, we'll plug in, got negative 6.67 times 10 to the negative 11th. The units there are meters cubed per kilogram seconds squared, times mass 1, we'll say is 65 kilograms, the mass of the person, times mass 2, running out of space, we'll come down here, times mass 2, that'll be the mass of the Earth, 5.97, times 10 to the 24th kilograms, times 1 over r, that'll be when the person is jumping upward. So when they're at the surface of the Earth, this is the distance from the center of the Earth. And now when they're jumping upward 1 meter, this will be the new distance, just slightly different. So that would be 6,371,001 meters minus 1 over 6,371,000 meters. And when we plug all this into the calculator, we get 637.7 joules. Compare that to what we got the first time, 637, no 0.7 joules, so pretty darn close in terms of the change in gravitational potential energy between the two equations. Now this one is certainly more complex to use, and you probably wouldn't use it if we're just talking about an object that's moving near the surface of the Earth. You'd use the simpler equation for that. So here we might do this when our distances are much larger, we're much farther away from the surface of the Earth, or maybe if we're talking about 2 planets or a planet and a sun and the gravitational potential between those two things. But anytime when our distance change is very small relative to the overall distance between these objects, this whole equation, it probably doesn't make sense to use. We'd use the other one.